Excellent. Morning, everybody. Today in the morning, we start with the second lecture by team.
Right. Yeah. Thank you so much, Alexei, for that. And there we go. Yeah. Thank you. Then I can. Thank you so much, Alexei, for the intro, and for all of you for making it in for yet another day of fun with EDS and this ongoing really interesting summer school. So basically, the aspiration, at least, is to kind of pick up the story, the narrative where we had left off yesterday. Yesterday, what I tried to do, at least, is give you some general sense for how the PDS are sort of defined and how they're used throughout both particle and nuclear physics, given the fact that this audience indeed is of a somewhat sort of mixed nature, if you will. Hopefully today I'll give you a little bit more of a clear sense for basically how the electron-ion collider comes into the story and plays, I think, a really important role sort of shuttling between, I think, lower to higher energy, where a lot of our interests, myself as a particle physicist, as I told you, is toward phenomenology at hadron colliders, places like the LHC, of course. So that's the idea today a little bit more. I'll mention a number of open issues in the parton distribution functions and related physics, especially hopefully areas where the electron-ion collider enjoys some special relevance. And then I'll try to connect things a little bit more to the specific implications at places like the LHC, the HEP implications, if you'd like. And as we talked about a little bit yesterday, of course, the magic that we use in this field is, of course, the QCD factorization theorems that allow us to calculate at a given sort of fixed order in QCD to very good modern theoretical accuracy now, many different processes of relevance at the colliders. And we had some good discussions in the recitation last night about some of these types of ideas too. But just taking a sort of generic example for sort of Drell-EM that goes to some final state lepton pair, as I tried to explain in some detail yesterday, of course, the idea really is that, how well I can do in terms of really quantifying and encoding uncertainties basically for the two colliding protons at the LHC really gives me a great deal of basically my precision and my accuracy, of course, in a given calculation, up to, of course, how well I understand the perturbatively calculable sort of hard partonic cross-sections that we also spend a lot of time trying to understand, up to some power suppressed corrections. And so that lets you calculate a process generically of this sort. So that's just sort of the idea. Now, how does all of this come into play, and why do we, as particle physicists, spend so much time actually discussing these types of things, these issues related to sort of the bound state structure of the proton? Well, it's because a great deal of what we do in particle physics is trying to understand the validity of our picture for sort of fundamental elementary particles in the standard model and beyond, right? So this is the sort of beloved pie chart that I'm sure I don't know, a good majority of colloquium speakers end up somehow gesturing at. So here you go as well. I'll make some reference to it also. A huge amount, as you probably know very well, of the enterprise in particle physics is now motivated toward trying to test this sort of basic picture, right? This idea that in the mass energy budget of the universe, in some sense, what we think we understand relatively well is actually a very small component, right? The so-called baryonic matter, which is the stuff that we as QCD theorists spend so much of our time trying to describe. And in principle, we know from various lines of evidence, right, the fact that there is some sort of dark matter through various lines of perhaps astrophysical observation, but then also, of course, the dark energy that's responsible for the acceleration of the universe. And so there's this mix of these different contributions. And what I like to say, it might be a little bit sort of facile, but I think it roughly holds, is that if you want to really try to search for dark matter to understand what might be going on in the other sectors of this really basic kind of pie chart, somehow we have to do better and better, really trying to control to good precision this tiny little wedge that we do somewhat understand, our ability to make predictions at colliders and elsewhere in sort of the baryonic sector. So there are a variety of ways that this goes in general. So if you're trying to search for maybe dark matter, just BSM in general, there are types of direct detection experiments. And this is incredibly high level, of course. I could spend an entire talk on any of these different components, of course. But the direct detection experiments are ones that maybe they're shielded deep underground and look for some sort of nuclear recoil that might come from some sort of like WIMP-like interaction, like a neutralino exchange that kicks the nucleus back. That's a direct detection experiment. There are types of indirect measurements like the AAMS, which is actually a space-based observatory. Or what you do is you basically try to look for anomalies in the spectra that might indicate something inside the universe that's not well explained by our standard model picture. Those are kind of on the side, but I thought I'd just quickly mention them. The stuff that we spend a lot of time doing at the LHC, of course, is collider searches for new physics in the particle physics sense, right, of new fundamental interactions. And the idea really there is basically to look for the unexpected in processes that we can measure and for which we can make calculations that are at least relatively reliable to the extent we understand them. And the idea is that that might be a sort of flag or a proxy for physics that we don't currently understand very well. So there are two kind of dominant paradigms. This is a bit of a simplification, admittedly, for how this sort of goes in general. They're the sort of bump-humped searches that you might know quite well, such as those that were responsible, of course, for the Higgs discovery in 2012, where you might look for basically some sort of resonant production of a new particle. In this case, there was already very strong indication that the Higgs existed and that it existed in something like the mass window where it was ultimately found at the LHC, of course. That's sort of kind of the discovery type of mode. That's kind of maybe the dominant paradigm that particle physicists used to think about things. There's also a more subtle approach as well, if you'd like, the sort of precision search. And I think that's the idea that motivates what I'm talking about a little bit more clearly, where the idea is you want to basically test the standard model very systematically by measuring things to greater and greater precision over many different channels. And I think I introduced this notion a little bit yesterday, at least in some detail. And the idea is that there could be some set of deviations from the standard model predictions that could reveal basically maybe a new pattern of particles or interactions beyond the standard model, right? And I think one aspect that I really want to emphasize for this lecture is the fact that there's a kind of global nature to this enterprise where in principle, one wants to amalgamate many different processes and channels to really do this in a systematic fashion. And I'll get back to that toward the end of the talk, sort of closing the loop in this area. But so, yeah, kind of the other side of the coin, if this was sort of the initial Higgs discovery circa 2012, the right-hand side is now trying to use the Higgs as a sort of tool to test the standard model and look for BSM in some way, where basically you're producing the Higgs through a variety of channels. For instance, the glue-glue fusion channel is the dominant 90% channel that I'll talk a little bit more about in a moment. But then there are various other sort of vector boson fusion, associated boson, et cetera, et cetera. And one can measure, of course, various final states. And the idea is you try to compare these different processes against the predictions that we have for the standard model, where in this curve, everything is basically normalized to the standard model. So things consistent with unity would say, okay, we're basically on firm ground. So that's kind of the general idea. And again, just to drive the point home, as I just mentioned, right, if I want to do this, I wrote this formula, of course, that I showed actually yesterday for just sort of like inclusive gauge boson production, WZ production, but the thing goes through again and again, right? I'm in general producing, say, the Higgs or any of these particles through the collision of two initial state protons at the LHC, and the PDFs are absolutely essential to my precision. And this goes through case after case in general. So a lot of what we'd like to say sort of standard candle, well-motivated sectors where you might try to measure things very precisely for signatures of BSM or just something unexpected, they tend to be actually really significantly limited by our knowledge of the PDFs. I mentioned just a moment ago, of course, the Higgs cross-section, but that's the case for many different observables. And I'm sure probably at least some or many of you have heard of some of these types of ideas, right? Maybe I want to measure some sort of electroweak couplings and it's encapsulated by something like sine squared theta W, maybe the W mass as well, et cetera, et cetera. And I think one thing that I want to emphasize is that tackling this is really a systematic problem. It's one that is, requires really a comprehensive approach. It's not simply one additional sort of theory uncertainty that you kind of tack on. It's something that really requires some kind of comprehensive effort. This is a little bit older, of course, but I leave it because it makes the point. I think one could show this in many different ways and in many different contexts. But just imagine you wanted to try to understand sort of the charge splitting of the W mass in detail. This can be measured, of course, in a number of different channels, maybe through different charged lepton tagging, essentially, for this process. There are various uncertainties that come into play, but what you can notice, if this is a generic example, it's actually the PDF uncertainty that can really be the dominant effect. And it's just simply an illustration of the idea that we grapple with in this area. So it's not just about, of course, what's the uncertainty in getting some sort of number. I thought I would also mention kind of a cautionary tale from the deep recesses of the history of this field that basically somehow PDF mismodeling can have real world consequences that can indeed lead one astray in some sense. So this is actually obviously a rather old plot from the mid 1990s. I remember those days, but many of you may not have been around. But there was a measurement undertaken by CDF in the mid 1990s, basically measuring the jet transverse energy in this particular process. And there was sort of an excess in this observable that was suggested to perhaps hint at the notion that the quarks were composites. And so there were it was sort of an anomalous measurement, and the suggestion was that, okay, this is a real signature possibly for BSM physics. But in fact, the ultimate explanation in this case was the fact that really the gluon PDF had been somehow mismodeled. So gluon PDF uncertainties are ultimately responsible for generating, our ability to basically take these data and draw some sort of clean theoretical interpretation from them regarding the tests of the standard model, basically. So there's this interplay basically between theory, meaning in this case, for instance, perturbative theory and our ability to do these calculations, and basically the precision of the data that we have, the HEP experiments, and as well as our modeling of the PDFs that somehow mesh and come into play collectively in this area. So that's just kind of an overarching picture of the thing. That's a little bit more of the motivation. And what I'd like to do, I don't know, for the next handful of slides at least, is go through a series of examples to try to give you some sense for how this goes in a number of different sort of flavor-dependent channels and so on. So I mentioned a little bit ago, for instance, about W production. So just to give you a particular illustration, keeping things in general not at the proper like theoretical working order that's typically used in modern analyses, but keeping things relatively simple to try to make kind of the high level point. One can write down, for instance, the W minus production, singly inclusive cross-section, the rapidity dependent cross-section, for example. And what you find in general, this is of course a charge current process. So actually this rapidity dependent cross-section, singly differential, depends actually on the behavior of, for instance, the D-type PDFs of the proton. And one thing that I also mentioned when you're talking about this sort of charge current process in general, it goes fairly systematically proportionally to sort of the quark anti-quark luminosities for the production of this W minus process. So in general, the sort of leading order expressions are always ones that go sort of like du bar, et cetera, et cetera. And what you find actually is if you're trying to do this measurement, for instance, at larger rapidities of the produced W, there's actually just through the sort of standard Born level type matching expression that I showed actually yesterday, what you find is that there's this very close dependence of the rapidity distributions on, for instance, the behavior of the D-type PDFs at relatively high X, that is at fairly high momentum fractions of the colliding proton in this particular process. And I thought it would be fun for this audience, given its sort of mixed particle nuclear nature, to stress the fact that somehow we still really struggle to understand the dPDF to the requisite precision for processes like this. And that's actually what's illustrated in this case, basically, where basically uncertainties in my ability to extract the dPDF really can lead to very strong deviations. These actually come from nuclear uncertainties that I'll explain in just a moment, especially at the very large rapidities that I was just talking about. And those, of course, ultimately can then translate into uncertainties in just sort of total cross-sections where we might really want to, do the precision sort of standard model test that I was talking about a slide ago. What exactly are these nuclear corrections that I'm talking about? This came up actually in the discussion a little bit last night. So of course, I don't have in nature a free neutron target, right? In general, of course, I can take a hydrogen gas and essentially, measure DIS off hydrogen. So that's actually something like indeed a free proton target. I can't do something analogous for the neutron. And the neutron is what's particularly informative about the dPDF, right? Just by isospin symmetry. So what we have to do is sort of the next best thing, right? So we might do something like deeply inelastic scattering on a deuterium target or on the deuteron, right? The deuterium nucleus, where actually now I can try to extract through tagging the final state recoiling proton, something like the scattering off the bound neutron. But in that case, you actually have some sort of nuclear binding correction that has to be modeled. And what I want to emphasize again and again is that there's very seldom, if ever, like a free lunch when you're trying to do this sort of modeling of the structure of the proton, right? We have to get data from various sources and then really confront those data with the appropriate theory. So if you somehow want to unbury your understanding of the D-quark PDF, we actually tried to get it from something like the neutron using isospin, but then ultimately you still have to include some sort of nuclear correction, even for the deuteron as a two-body bound state, right? The fact that the baryon is somehow relativistically moving in this two-body state. And what this plot illustrates actually is actually just the extracted actually ratio of the D over U PDF at high X, depending on the choice of somehow the treatment of this nuclear correction. So what I'm trying to tell you is that there's this sort of cascade or tower of corrections that can propagate from modeling this kind of low energy process that maybe nuclear QCD people spend a lot of time thinking about, all the way up the chain in a sense to our ability to predict gauge boson production at the LHC. And this happens again and again, actually. So this is really a high X effect. I think is something of kind of a complement to some of the lectures and discussion that we had about low X physics, which is very much a crucial subject as well. I would emphasize that things are not all well and good at high X either for various reasons. In general, it's very hard to access it kinematically. At high X for the PDS, you're in something very often like an extrapolation region where really subtle modeling issues can have a significant effect and propagate into quite different behaviors. And this is actually something, again, that came up, I think, in the discussion last night, as well as in the Q&A yesterday morning, where we might try to take various parton distribution function analyses that are kind of on the market and try to inter and cross compare among them to understand their systematic differences. And this was the last such exercise that we did in the kind of HEP community is called PDF for LHC, where we take the PDFs from one of my groups, the CTEC-T collaboration, as well as MSHT and NNPDF, the neural network PDF group, and try to really boil them down to be as apples to apples as possible in terms of their internal methodological assumptions, as well as the theory that we put into them. And what this is meant to show, maybe this is a little bit complicated, but what we did is we sort of transformed things a little bit, where basically what we were doing, that's what this scaled means, we're plotting the U and S PDFs going to fairly high X, where actually you weight according to the sign of the PDF. And what we find, and this was only something we discovered almost on the fly, is that some groups actually sometimes even have, they don't have a positive definiteness requirement on the high X behavior of the PDFs, such that the PDFs can go negative at very high X, which, okay, that's fine. Observables had better be positive definite, of course, but you can get these sort of curious behaviors of the PDFs. And in any event, what we find actually is, so imagine you take this set where you don't actually truncate the PDF to be restricted to be positive definite, and you go and you calculate something like relatively high mass Drell-Yan, like that sort of factorization theorem that I started the talk with. And you actually, depending on this sort of high X behavior, can get fairly different sort of behaviors now in this invariant mass distribution for the final state Drell-Yan lepton pair. And what you find actually is that you get a very specific prediction in that case, but if you allow this, loosen this restriction and get this wide range of sort of funky high X behaviors, you get a very, very different prediction. So there's really this important need to constrain high X, even when you're talking about very, very high energy collider processes. You might naively think, high energy, that's really, really low X. In general, if you're talking about observations like invariant mass distributions or certainly rapidity distributions, as I was talking about, those can probe actually the tails of the PDS to quite high X. Incidentally, very often where we're actually trying to look for signatures of BSM physics. So it's really, really an important matter that we continue to deal with. I don't have time to go systematically through every possible example, of course, but just as a proxy, that's, I think, a relatively good one and certainly a process that still attracts a huge amount of interest. I mentioned the Higgs sector, which is where a huge amount of effort goes these days in testing the standard model, as I mentioned. The dominant channel for producing the Higgs is sort of the gluon fusion channel, which is 90%. And there are various others, as I alluded a little bit earlier in the talk. And I'll show, I think I'll sort of toggle between a couple of slides. In general, what you might try to calculate is something like a parton level luminosity, which many of you may have heard of, and I think we talked about briefly in the discussion yesterday, where essentially I can imagine calculating sort of, all right, I have a total beam luminosity in a given experiment, be it the EIC or the LHC, PP. And I want to think about, okay, what's the effective rate in terms of the collisions at the parton level? And I basically can go from the gluon PDF to some sort of gluon luminosity that I would somehow convolute with basically the overall luminosities of the experiment. And it's fairly straightforward to compute that quantity as a function of the gluon PDS. In this case, maybe sort of at the physical point for Higgs production. And what you find is actually there's still a great sort of residual uncertainty at the latest complete theoretical accuracy in QCD, which is still next to leading order in general. So depending on sort of the set that you use, you can get these significant variations in sort of the total Higgs production cross-section through this sort of gluon mediated channel. So you get, again, this propagation not only of the statistical uncertainty released by a given global fit, but just one also that is realized through sort of methodological approaches to determining the PDS as might be represented in the spread as an example. And so, yeah, where does that come from? Again, it significantly comes from our ability basically to calculate the gluon PDF in the Higgs sort of relevant region, which is something like 10 to the minus 2, so 0.01 value of X, and at the virtual at the scale corresponding to sort of the on-shell mass of the Higgs boson. That's sort of roughly reflected in this plot, which is from one of the recent global fits that our group put out a couple of years ago. So again, somehow this propagates through to the glue parton luminosities that I showed before, and then ultimately informs the total cross-section. One thing you might wonder about is, okay, how exactly do I try to control this? And this reflects kind of the discussion that we had actually yesterday about, okay, I want to understand what types of data do I really need? What experiments are particularly sensitive to particular, not observables, but actually to the PDS in a given regime that might really control a calculation like that for Higgs production. And it's actually something of a mixed bag. And this is something we really grapple with. So sorry, I keep jumping between the two of these. I might, again, want to really think about, okay, what are the poles of various data that I fit actually in a global fit? So fitting the gluon, but indeed all of the parton flavors simultaneously. What are the experiments that might have particularly strong statistical pulls on this behavior? And that's where we sometimes really indeed wonder about the compatibility in our treatment of various of these data sets. So what this is illustrating in this panel, I showed an example of this actually yesterday, but it's really it's a plot of the gluon PDF at that sort of value roughly that I was just showing on the previous transparency, where the heavy black line is the shift from the optimal chi-squared of the full fit sort of combined over all of the data sets that are described, and then separately kind of broken down among the various leading experiments that might have particularly strong pulls on the gluon PDF. And this is this so-called Lagrange multiplier approach that I mentioned a little bit ago, where essentially I impose a constraint on the behavior of the gluon PDF at this point, and then sort of dial it continuously one direction or the other, refitting the other degrees of freedom to try to understand. So essentially, I'm taking some sort of trajectory through the parameter space of the PDF fit, with this as a constraint, hence the Lagrange multiplier notion of this approach. And what you see is that there are sort of shifts in the chi-squared experiment by experiment that can sometimes differ quite a lot. So for instance, actually something like E866, just the absolute cross-section, proton on fixed proton. So that's a fixed target Drell-Yan measurement at not low energies, but lower energies certainly than what are relevant at sort of the multi-TeV scale at the LHC. That might actually somehow really prefer a much harder value of the gluon actually at this particular value for the Higgs point. But then maybe some of the newer jet production data really dislike such a shift. So there's somehow this competition and curious pulls that bear partly on how we treat these various experiments. And one remarkable observation that I really stress, and I think is important just ideologically to this talk, is the fact that you get this sort of behavior, right? So the fact that incredibly, I have relevance to Higgs theory or whatever it is, very high energy phenomenology from all kinds of curious things. There's the Drell-Yan cross sections that I just mentioned, but even things like neutrino nuclear scattering, where we get important constraints not only on the strangeness content of the proton, but also the coverage over a variety of scales can be very informative to the gluon density as well. So that's something to really keep in mind, both for this talk and then just going forward in general in your research, I would say. Are there any questions, or should I just keep going? And just feel free to jump in if you wish to ask anything, because I know it's quite a lot of material. We'll just see how far we get. So this is a little bit more of the same, effectively. So the fact that these global fits constrain many different flavors that in turn inform the predictions for different collider observables are such that we might really try to squeeze things and do a great deal of phenomenology on the fly as we determine these PDS in proper global fits. And this is, again, just kind of an illustration using various modern next to leading order QCD tools to calculate things like TT bar production at 14 TeV against the gluon fusion channel production of the Higgs that I just mentioned. What you see is basically this sort of spread that corresponds to various treatments of the PDS. So there's, again, I keep trying to say, I think this was something that had come up in the discussion yesterday. You have a given extraction for the PDS with a given nominal uncertainty. Never be satisfied with just that, right? Because what you can find is even more apparent in the right-hand panel that actually correlates basically W production against Z production, where these are actually maybe sensitive to different internal flavors in the PDF analysis, is that actually a single modeling choice in the PDF global fit can indeed have a pretty pronounced systematic shift in the prediction for this process. And it makes a shift, so these ellipses are sort of tilted in a certain angle that actually is very closely related to the parameterization that we use. But what you find going from this sort of heavy black curve, which is the baseline nominal, what we called CT18, up to an alternative fit, CT18Z, which differs perhaps most crucially in the fact that it includes a set of data from Atlas at 7 TeV for the production of W and Z data that actually pulls up the content of the nucleon, the strangeness content, and actually can shift the prediction really quite notably. Yes.
Oh, sorry. I was
Yes.
just finishing the yogurt, but I can't be here. But for
Yeah.
these,
Yeah.
that what you have in there, those are let me see if I understand. You're using the same
Yeah.
PDFs for both?
It's for both panels.
Yes.
Yes. Yeah.
So then
Yeah.
here's where I struggle, right?
Okay.
The idea is that they're universal, but then you'll explain one better and then not the other. How do you bridge the gap? Is it this idea that yeah.
Well, so there's no, I think this might help. So there's no direct comparison with any data in this. So these central points are actually just the best prediction, basically. So there's no, the point I'm trying to make is more sort of the statistical compatibility, if you will, among these different predictions, not to, so in practice, you could actually, and maybe this is something we should have done, you can actually, of course, say like, okay, this is, maybe the global mean prediction for this like total cross section, which, I mean, in general, the prediction, of course, is there's a circularity to this, as I mentioned yesterday, because the prediction is itself like PDF informed. But the point I'm trying to make at this level is just more the fact that these depend on the PDS and can shift. And
Okay.
yeah,
Sorry.
yeah, no, that's like, I thank you for asking. Okay, so that's sort of that. So I think this is all kind of at the level of total cross sections for the most part. And one other thing that I wanted to mention is I don't think it's explicitly made clear on this, but the fact that what I said in words, these are all next to leading order QCD predictions. And so we spend actually quite a lot of time worrying about, okay, going to the next fixed order in the calculation, the next highest order in alpha sub S. But at some point, and I like this, and I think I don't know, I worry that it's very complicated, but it's still sort of a cool point that I think this audience would hopefully appreciate, is the fact that at some point, if I judge it's necessary to include sort of higher order QCD corrections, at some point, it doesn't make sense to continue squeezing things more and more in one particular sector of the theory without correspondingly including higher order treatment of other things that might matter, like the electroweak corrections. And what curiously happens actually in this case, so if I'm thinking about maybe another added surge channel like associated Higgs production. So that means in this sort of charge current case, actually Higgs plus maybe W plus. If I think of the pure QCD process, it's again this kind of Drell-Yan-like process that's dominated by the QQ-bar that I alluded to a little bit earlier. That's obviously an essential contribution. But if I want to predict this particular process, say at 13 TeV or 14, whatever the case is, and I want to examine basically the behavior on the invariant, the dependence on the invariant mass of the combined two-body system, at some point, if I include the electroweak corrections to try to have better theoretical accuracy, having that additional coupling is such that at that order, I can now have an explicit contribution from the photon as an initial state of the proton. So that then mixes in yet another component to the calculation, the fact that I can not just be dominated entirely by Q-bar scattering, but now through this kind of curious quark light sort of scattering process. And then again, I still have the usual electroweak sector couplings that give me the final state W plus Higgs. And what you find is there's actually a very small negative correction at the exact kind of on-shell point for this process. But if you're trying to understand the physics and the behavior of this process at sort of larger invariant masses, actually this turns on and predominates such that the electroweak correction is really, really quite important. And what ends up really mattering is then my ability to model and understand curiously this photon PDF that is a contribution to this process. And somehow this comes up again and again. Previous summer school, it came up, and I'm going to mention it again because during our question and answer, or the recitation rather, last night, we talked about it really at quite some length. Again, this question of what really is a parton and what are the parton distribution functions? You might naively think it's the quarks and their gluons, right, in the proton. And again, as I like to emphasize, the PDS and the associated global analysis confront the full standard model and actually conceivably even BSM physics at some point. So at some level, of course, the fact that the quarks are electromagnetically charged, they can radiate photons, you can resum them into a photon PDF and actually calculate it. And a fairly recent innovation in this area that I wish I could go into in more detail is you can actually calculate the photon PDF given your knowledge of just the good old fashioned F2 and FL structure functions of the proton, knowing their behavior over a wide range in Q squared. There's a really curious matching calculation where basically what you do is calculate sort of like the heavy neutral lepton, a fictitious process, heavy neutral lepton scattering from sort of the electromagnetic field of the proton in some sense. And you can calculate that in a kind of hadronic tensor approach and then match it to a similar calculation with an explicit PDF. And that's how you basically unfold this horrendous expression, which is actually not really that bad as things go, and lets you calculate the photon PDF as a function of X. But crucially, you have to integrate over a huge range of Q squared of the structure functions of the proton. And this actually is very helpful because believe it or not, despite the spread, it reduces the uncertainties to sort of multi-% level. But the fun thing that I wanted to mention, and again, you'll notice there's kind of a refrain. I keep returning to the same basic point, is that the fact that I have to understand these structure functions down to quite low Q squared. I integrate these things very, very, over a full allowed range from the so-called master formula. What it does is it introduces then a dependence of the photon PDF in this calculation on actually fairly low Q squared sources of information on the structure functions. So things like the electromagnetic form factors in the limit of x approaching 1, for example, but also all kinds of funky things. The twist 4 contributions to the structure functions, resonance processes as well, maybe how exactly I adjust for the actual finite mass of the target, the proton target in this. So again, there are all these really weird sort of loosely non-perturbative QCD effects that ultimately end up propagating to higher order phenomenological calculations, like this associated boson production that I mentioned. And again, the EIC is really crucially tuned to this kind of physics, right? So I mean, the EIC is really ideally focused on things like, but not just low X, but also high X as well. Trying to understand to greater precision and accuracy things like the higher twist and target mass corrections and how exactly these all really work out. And what you find is, including for like a charge current process, maybe measuring just the structure function of from W plus charge current interactions on the proton, these effects can be really, really significant. So if this is basically just a plot of the correction of now a target mass effect. What you find is that this is really something that's quite substantial and that you'd like to really have good fidelity in trying to model it. So I mentioned a bunch of these different things. Are there any questions? Because I'll now shift to now the EIC component of a little bit more explicitly. Yeah, so I'll just be brief on this point because it's of course like a huge focus of this summer school. Okay, what is the EIC? What is the point? I perhaps somewhat simple-mindedly, and this is a reflection of my own personal background and perhaps bias, think of the EIC effectively as an even higher luminosity incarnation of Hera. And you'll remember, I should say, that yesterday I showed, okay, we've got all of these data sets that inform the PDS. Hera, which I plot again here and shamelessly stole this plot basically of sort of the kinematical coverage of some of the important experiments that we care about, really still kind of dominates the landscape and is really as a source of DIS collider information, really is really important in pinning down the gluon PDF and all these other things that we care about. The EIC, of course, extends that picture. It's much, much higher luminosity, very, very good statistics. And it also, I think, something that's really exciting, given what I just mentioned a little bit ago, it extends our ability to probe, if you'd like, the quark to hadron transition region, and that you can traverse from sort of lower Q squared up to really quite high values of Q squared to get a better handle on QCD evolution and understand the turn on basically of some of these non-perturbative effects that I was just talking about a moment ago that are crucial for the pheno applications. I'll just quickly flash this. This is a little bit older, but exactly what does the EIC have to teach us? Of course, you can do all types of different measurements at a DIS collider. Just for the so-called yellow report that we worked on a handful of years ago, basically, we spent some time trying to understand the PDF level impacts, basically of just EIC pseudo data, starting with where else but just the inclusive channel. So just inclusive, deeply inelastic scattering, no real final state tagging, at least hadronically or anything. And what you find, there's obviously, of course, some dependence on the chosen framework and so on, but this really, even the inclusive data, of course, is really important to our ability to extract the PDS. I take a particular example from one of our own analyses, just even something that's relatively well known. The behavior of the up quark PDF, again, it's something comparable to the traditional starting scale in one of our global fits. What you find is if I take kind of a fit where I might remove all of the historical fixed target deeply inelastic scattering data, places like BCDMS and so on that I mentioned a little bit ago, that's the blue band. And then what I can do is do this exercise of restoring that body of very informative information going back actually decades and get this sort of green band where I put things back in. And then alternatively, rather than doing that, the red is then just taking sort of the inclusive EIC pseudo data that I just showed. And what you see is that particularly at high X is one example, low X2, that actually that body of EIC just inclusive information can actually outstrip the constraints from all of this so-called legacy fixed target data. So very, very informative just at the level of inclusive observables. Of course, what you'd like to do, however, is not just that. You'd like to use the full series of lever arms empirically that the EIC or any experiment can in principle afford you. So maybe I want to try to get specific measurements where I'm not inclusively summing over many different parts on level channels, but I might have some ability to kind of tag the final state in a way that might give me particular sensitivity to the strangeness. So I thought I'd quickly allude to a calculation we did a couple of years ago on that front. I'm not going to spend much time on it, but you could do charge current DIS. So, I mean, this information, this plot rather, it comes from partly charge current inclusive scattering, but you could similarly do charge current scattering on the proton at the EIC involving W- exchange, but where you tag maybe a final state charm that through this charge current process then is ultimately sensitive to the strange content of the proton. What you find, I'm not going to go through the technical details so much here, but what you find actually is that in principle, such a measurement is indeed really sensitive to various scenarios for the behavior of the strange and greatly, greatly outstrips the current modeling uncertainties that we have for the strange content of the proton. So you'd really like to have these types of various additional channels. That's for the strange content. Another example that I'll just quickly flash, not really belabor this, we mentioned it briefly yesterday, is the charm content of the proton. This is this kind of curious aspect that has gone back actually a number of decades that I think the EIC can hopefully finally really resolve. We saw yesterday, I think it came up in the question and answer briefly, that actually the charm PDF is in typical PDF global analyses assumed to be generated perturbatively, essentially, so that it ends up peaking at relatively high X, of course, and being really quite small, and tends to be, in many phenomenological applications, relatively negligible. But in principle, one could take the same sort of modeling approach and actually flexibly parameterize and fit the charm PDF much on the same footing as you do for other contributions. So in that scenario, instead of assuming that the charm is generated completely radiatively, and that's the scenario in which we take maybe a starting parameterization charm is identically equal to 0, instead of that, we use some sort of flexible form, right? Now, the question is there actual genuine sensitivity to this scenario in the global data set and with the theory that we have at our disposal? And for that reason, you can't just immediately throw in the most flexible form you have at your disposal. What you do is take a representative series of behaviors and might then try to constrain the normalization for those to see, is there any sensitivity to this whatsoever? And that's basically what is done in this particular calculation. I'm not going to go through this in great detail, but that's at least just the gist. One can take, assuming some sort of like quote unquote valence-like, which is to say a relatively high X peaked shape for the total charm distribution at something like the starting scale, one can take a given shape and then basically tune the overall normalization as quantified by the first moment of the distribution and examine to what extent is the global data set actually really sensitive to this. And this is another realization of basically what I showed a few slides ago, where you're basically just looking at kind of chi-squared variations and is there a clear preference statistically in the global data set for any of these behaviors. What you see is there's the tiniest kind of hint of some sort of preference for a non-zero FC fitted charm, but it's very, very small. And the preference is very small relative to sort of the typical thresholds that we set statistically where we say, okay, this is really a preferred behavior. So the jury is somewhat still out on that front. You might think, okay, why do I care about this? Actually, there are various different channels that at the LHC that in principle can also be sensitive to this sort of thing. One example that I just take more or less at random, but it's certainly a relevant one, is something like Z plus charm production. There are actually data on this process at LHCb that are intriguing, but then actually truly exploiting these data might require things like parton showering or better treatment of the perturbative QCD sort of uncertainties, if you'd like. And what you find is, in general, if I'm doing a measurement of this type, here's our beloved formula for the sort of Born level matching, and I examine the rapidity of the produced Z, there might be some very small, perhaps at larger rapidities, preference for a non-zero fitted charm. But again, I think in general, we still need to do better with these data. So there are various examples of this. The electron-ion collider, in principle, I think would be a really ideal place to try to get a better handle on this sort of question. The EIC is a platform where you can imagine doing sort of the tagging that I mentioned a little bit ago, or also just examine sort of the Hayek's behavior of the structure function. And in general, what you can find is that even in the inclusive data set that I mentioned a little bit ago, you actually do indeed have some relatively good sensitivity at sort of the data level to the behavior of the charm PDF. So in fact, the hope is that really that we can get good information from the EIC and perhaps finally truly have enough constraining power in the resulting global data set to try to actually resolve these types of questions. So it's a very, very good platform to do that. I wanted to just very quickly allude to the fact that there can be some interaction between empirical data from the EIC down the road, as well as constraints that we might get actually from lattice QCD as well. And I know actually there were a couple of dedicated lectures from my colleague Marta on that subject, so I'm not going to go on and on about it at length. But the question is, indeed, we would like to really try to understand how to interface these two things in detail. How do you take data from the lattice and actually incorporate it into global fits? How exactly do we try to really develop strategies for understanding the validity of lattice data in the global fits, using the global fits as a mode for doing so as well. So this is something that we've been working to try to develop, and definitely would be very happy to discuss it further during the Q&A or during the recitation. So the very last thing that I'd like to get back to, I can go on and on, of course, about perturbative accuracy and doing better just on the pure theory side. What I'd like to very lastly discuss is this curious question about the sensitivity to BSM physics. Again, as I started to motivate the talk, that's really very substantially our motivation at hadron colliders like the LHC. Not only is the EIC a very good machine for, of course, trying to extract and understand nucleon structure as parameterized by PDS as well. You can, of course, understand couplings, and you might even try to test the standard model at the EIC in a way that is indeed complementary to the LHC, or equivalently could also inform LHC measurements as well. One thing that I just mentioned before turning to that subject is the fact that, okay, very often what I'd really like to do is some kind of simultaneous determination of both the PDFs as well as the couplings. The most obvious choice, of course, being just the alpha sub s, the strong coupling, of course. And even the inclusive EIC data could help us there. But a little bit more immediately relevant to perhaps BSM phenomenology, or at least our understanding of the electroweak sector, the EIC pseudodata could actually be an important, well, we've tested this with the EIC pseudodata. The EIC program itself could ultimately be very helpful for understanding just electroweak couplings in greater precision. And I show this as a representative example for just the sensitivity to sine squared theta W, for example, just from the, again, I keep pointing at this sort of inclusive EIC data set. Why would I care about this? Well, of course, and you'll notice, at least I hope that you'll notice that I've built this up kind of piecemeal, going toward grander and grander sort of things. In principle, what we really think to try to do in this area is to try to understand how exactly, imagine you have some sort of undiscovered BSM physics. Maybe it's very, very heavy or very massive, living well beyond the electroweak scale, but that in some way imprints itself as a proxy, essentially, on sort of the parton level couplings, the electroweak couplings. And one example where you might try to really investigate this at the EIC is through something like parity violation, of course, where I might have I have, I can define a beam helicity at the EIC using the helicity of the colliding electrons, and I can actually measure an asymmetry on that basis. And what I can do then is write things at the Lagrangian level in this sort of effective way. I'll maybe talk about this a little bit more in the next couple of slides, but I can write down kind of an effective, if you'd like, essentially a 4 fermion interaction where the overall electroweak interaction at parton level is encoded in these individual sort of numbers, these individual electroweak effective couplings. And the idea is that I can basically try to extract those from the parity violating asymmetry. And again, as you'll, as you may have guessed at this point, of course, my ability to do that, these things are buried in these effective combinations that themselves, writing things just, of course, at leading order in this case, also depend on the PDFs. So if I can determine the PDFs jointly very, very well, then in principle, I can also try to determine these effective couplings that weight these sort of effective 4 fermion interactions. And we can talk about that a little bit more in the Q&A. And so in turn, I might use this to try to actually extract sine squared theta W, or I could do even more global things, as I'll mention in a moment. And with that information, I could actually test a variety of different BSM models and scenarios. One might be something like a leptopork scenario, which is a specific modeling assumption. And here I want to mention that what's often done in HEP is something that had been done historically, actually for many years in QCD modeling, where often what one would do is say, okay, I want to model whatever the case is, maybe the gluon density of the proton. And so somebody wrote down a particular model that they liked for some reason, and here's a particular data set. And what you would do is you would essentially then try to test that specific model. And of course, the global analysis paradigm that I've talked about now is somehow a generalization of this approach, where I try to flexibly parameterize the PDFs and then confront a global data set. One can, both approaches are actually somewhat valid. On the BSM modeling side, what particle theorists have done actually for quite a number of decades now is say, here's a particular model. I obtained it on the assumption of some sort of group symmetry arguments or something like that, or it's just a model that I like. Here's a Lagrangian, I've written it down, and I'll try to constrain maybe the couplings of that model using a particular data set. And you can do that, and it can in fact be informative. But ultimately, what we want to do is actually generalize things away from this really specific model-dependent approach, albeit it's one that you can indeed test at the EIC, as I was just saying, in a particular measurement like parity-violating electron scattering. Just going to skip this. But what we're moving toward in this field, and I wanted to mention this specifically because I think it's in previous realizations of these summer school lectures, there would often be actually a dedicated series of lectures on the topic, so I'll still just quickly mention it. What you might try to do is take some systematic approach, if you'd like an effective field theoretic approach. One such approach that's enjoyed a good deal of currency lately in particle physics is the so-called SNEFT, the standard model EFT. And the idea, of course, is that you have a systematic expansion where the sort of the leading contribution, in a sense, is just the standard model Lagrangian. And then I can write down a series of operators that I organize systematically based on the dimension of those operators. So the dimension 6 operators, incidentally, the sort of 4 fermion interaction that I just showed is one such example. It's explicitly 4 fermion. And what I do is I write down every such combination that I can, weight them by some sort of Wilson coefficient that's then power suppressed by the BSM, like new physics scale, and then try to use all of the data at my disposal to fit basically the normalizations for these various operators, the C's, if you will. And the idea is that actually what we would really like is to have many different data sets to solve this independent, separate inverse problem. It's a global fitting approach, not unlike the determination of the PDFs as well. And so this is something that we're really trying to pursue and understand in this area. I mentioned a little bit during my talk yesterday that one of the questions is like, okay, these types of BSM global fits undertaken through the EFTs that I just mentioned, there might be a kind of inherent circularity, because what you're trying to do is trying to fit these C's based on data that you have, hadronic data at the LHC, it could be data at the EIC for that matter as well. And what people have very often done is treated the standard model baseline for these types of EFT fits using the frozen PDFs that are extracted often from many of the same hadronic data sets. So kind of a frontier in this area is trying to expand things somewhat and investigate to what extent might there indeed be some sort of correlations between, if you'd like, the nominally BSM sensitive coefficients that weight these types of operators in the EFT expansion and the PDFs. And so far, I mean, there are hints of correlations that I alluded to a moment ago, or actually yesterday, I should say. But those correlations are such that I think things could get stronger and stronger as we weight these data. This was actually for TT bar and jet production data. As you increase the luminosity or get more and more of these data, basically you could get more of a systematic effect from doing the simultaneous global fit. Okay, the last thing that I'll just quickly mention, particularly because I think we have some tutorials later today and later on in the week, is the fact that what you may have noticed I'm talking about is somehow more globally confronting this large set of data that we have. It could be from the EIC, it can be from the LHC. In principle, we would like to take all of the data that we have and really try to understand them, flexible modeling approaches, et cetera, et cetera. So somehow, if you'd like, the big data moment has somehow arrived in some sense. So there's a hunger or a desire to look for novel approaches to try to do these types of analyses. And I wanted to just, this is just sort of gesturing, and hopefully it might bring up possibly some discussion during the recitation a little bit later. There I think is a great deal of interest in trying to get novel approaches and novel tools to do these. I mean, in many cases, I think the PDF global fits, as an example, have, you know, there are variations, of course, in terms of the methods and the approach, but very often I've given you hopefully a reasonable sense for how this tends to go. Like I ultimately write down some sort of parameterization, even if it's a neural network, it's usually parameterized at some starting scale. Okay, I've got perturbative theory, I evolve things, et cetera, et cetera. Can we do various other things that might be relatively new in this field? And I think there's a good deal of room to try to do this. I just show a few examples just from a couple of studies that have been relatively recent. One might be something like Markov chain Monte Carlo to try to do some sort of detailed exploration of posterior distributions and some multidimensional analysis. There's something like kind of the fast methods. This is a version of sort of the chi-squared polls that I showed a little bit earlier in the talk and somewhat yesterday. There might be something like kind of higher dimensional data embedding as well. And the idea is that you want to somehow try to marry all of these different approaches with you know, computational power and so on, and hopefully in a way that allows good reproducibility. As I keep saying, I think there's a good deal of room to try novel and sort of weird things, that it's not just saying like, here's just a technique, does it help, or does this speed things up, but it might actually provide an entirely new paradigm for trying to think about doing the global PDF extractions. I just wanted to show, I don't think I have the reference, unfortunately, but I'll add it to the slides. A recent study that we did in my group at Argonne, where you might try to, instead of this approach that I just described a moment ago, the kind of standard paradigm of parameterizing things at a starting scale, evolving, and so on, maybe trying to use some approach like an autoencoder, maybe to try to reconstruct the PDFs and have a new approach to the inverse problem in a way. And the idea of an autoencoder is, I'm not going to go into this in great detail, but and this is just simply one example. There are many, many examples that we could talk about, and I'm sure there'll be more later today. I might try to have some initial, as we say, feature space that is informed by the X dependence of some input PDF as one example. And then I have a cascading series, basically, of feed-forward neural networks that ultimately encode some very complicated higher dimensional representation down to something relatively small. So it ends up being a kind of dimensionality reduction approach. And then what you have on the opposite end is some sort of decoding algorithm that's basically exactly the same thing, but a mirror image that then takes some compact representation and then decodes it back to then some richer representation to basically the original X-dependent distributions that I trained on. And there are many, many possible complications to this, or elaborations, I should say. But the idea basically is that you want to reconstruct the X dependence of the PDF in this approach. And this is something that we've tried out as just one example to see, you know, can we roughly do this? The fun sort of example that we took in this case was saying, let me build this type of structure, but somehow force this encoding, this sort of internal layer, to have a particular physics structure. And what we chose for that was actually the Mellon moments, basically. So the lattice calculable moments of the PDFs in that internal layer. You train the model, and we did to sort of a toy example in this case of just sort of the SU2, the U and D PDFs. Encode them in this autoencoder representation in terms of their latent space, in terms of their Mellon space behavior. And then once you've trained this, then you give me a series of Mellon moments. They could be, for instance, maybe from a lattice QCD calculation. And then from that information, I can basically then decode basically the X dependence, the full X dependence of the PDF. So it sort of works. This is a proof of principle. One can continue to systematically improve and understand things, but this is really weird, right? And one of the advantages of this is that I can encode many, many different scenarios for how exactly do the PDFs, does their X dependence really, can it be encoded in terms of the Mellon space behavior? So it's just one example. I just took it more or less at random. There are many others. Please ask during the recitation. I think it would make for some fun and interesting discussion. And I make it to somehow stress the point that there, I think, are many options and opportunities in this area. So with that, I'm just going to go ahead and conclude. Thank you, of course, for going on this journey with me on the PDFs. I think the field is at really an interesting moment. One of the things that I want to stress is that I see the EIC as playing really a crucial role. The PDFs are kind of a shuttle that go between relatively lower energy QCD all the way up, as I mentioned and started the talk, up to the electroweak sector and back again. If I think we're going toward this era of trying to quantify things and somehow globally simulate physics at this level, I think there's a lot of room to include the EIC, but to do so using novel tools, both on the theory side, computationally, and so forth. So I think somehow we're over time shifting toward this more sort of global treatment and many, many opportunities to get engaged in this. The PDFs, again, as I keep trying to tell you, it's somehow all of our understanding of fundamental particle and nuclear physics somehow can be poured into the PDFs because we have to understand this global data set. I mentioned all kinds of sort of vignettes as I went through. I mean, there are all kinds of things to do. So if any of this struck you as particularly interesting, please obviously come up and talk to me while I'm still here. Also, just feel free to reach out. Don't be a stranger, as I like to say, and thank you. Yeah. Yeah.
More about this standard model effect in field theory.
Yeah.
What is the purpose, I guess? So it's something like SCAT, or is more like to...
Yeah. So I can, maybe while I talk, I can go back and gesture. So I tried to say this a little bit in words, and somehow this was meant to kind of counterbalance. Okay, I can, I don't have it on the slides, but I can write down a specific model, like a specific Lagrangian. The language of this field, it's a complete Lagrangian that we'd say is complete in the ultraviolet, and it's a complete field theory and all of this, but it's a very specific model, right? So, I mean, the aspiration I was trying to say is like, I want to write down in a way that I can systematically organize every possible higher dimensional operator that is inherently BSM in some sense, and do so in a way where I have a kind of perturbative expansion where the idea is like, okay, the BSM lives at very high energies, essentially at sort of the TeV scale and beyond, which is indeed a modeling assumption that I think should be stressed, right? I mean, this EFT approach, at least the SMEF does not, you can't, incorporate every possible model in this approach, but a huge array of possible models that live at high energies can somehow be mapped basically to some basis of operators. That's actually a huge enterprise now. A lot of my colleagues work on that specifically. And the idea is that in principle, you're somewhat more model agnostic, right? In the sense that, oh, I'm just testing, here's my, favorite sort of supersymmetry model, and I'm going to try to exclude this with a particular data set. Let me not do that because it becomes very untidy. Let me instead write down every possible operator at a given fixed operator dimension, where this dimension 6 is for the most part, up to caveats, is sort of the first non-trivial contribution, essentially. And then try to constrain basically the normalizations or the weightings for each of these. And the hope is that what you would do is you would take, just like the PDF global fitting, you would take a global data set of hadronic data from the LHC, from the EIC too, actually. You can do the same sort of exercise. And then actually flexibly constrain and tune these basically, these coefficients that weight the operators. And imagine that there is some pattern of deviations in the C's. The idea is that could then, you'd say, okay, this particular operator, you could actually then match that pattern to some specific model, and it would somehow do the work for you and maybe pointing toward the actual underlying, like, concrete new physics scenario is the idea.
So it's kind of like expanding the standard model as much as possible and see what works and not what doesn't.
I think that's relatively fair to say. Yeah, I mean, you think of the standard model as sort of a limit of this perturbative expansion, essentially, but it gives me a systematic expansion that I can use to try to test the standard model. Maybe is one way of kind of putting it concisely. Doesn't do too much violence to the idea. Yeah.
Yes, thank you.
Yeah, we can talk about it more.
I'm allowed to ask a question.
Sure, because
So the plot you showed last time and also today, the PDF divided by the standard model PDF.
Yeah.
I know, like maybe one slide before.
Yeah, sure. I think this direction, this thing.
So if I'm reading this right, the
Yeah.
deviations are largest at large x and the small x,
Right.
where fixed order deglap evolution, of course,
Yeah.
is known to not work very well because you need resummation.
Your favorite
So the
subject.
question
Yeah.
that begs itself to be asked is, how do you know that you're seeing new physics as opposed to just shortcomings of a fixed order deglap approach?
I think if there's a takeaway from my talk, it's that I don't think you do. I mean, I think that's exactly. I mean, I think you missed the beginning of my talk when I showed the cautionary example of sort of the jet mass CDF measurements, basically from the mid-1990s, that were taken as a hint of quark compositeness, when in fact it was actually just the gluon PDF mismodeling. Yeah, absolutely. It's entirely plausible. That's somehow exactly what motivates this type of work, right? Is that I could very easily go astray. Indeed, maybe I don't have the correct treatment of the low X physics, and then I do some calculation and I look, here's BSM, and that would be totally nonsense, of course. So in principle, what you want to do is try apples to apples to do an honest calculation and actually quantify. That would actually be a really interesting thing possibly to study, Uri, I think. But no, indeed, yeah, that's actually what keeps us up at night, that you would be drawn to a wrong conclusion simply because of one's inadequate treatment of maybe, yeah, indeed, yeah, maybe I don't have sort of the low X, log 1 on X resummation, and that sort of shifts things, but then that completely swamps my little signature that would have hinted that, okay, there's some sort of BSM lurking at low X or something. Yeah, absolutely, that would be bad, but very possible. Yeah. Yeah.
Why did you choose to use regular autoencoder instead of, for example, a variation of autoencoder?
Yeah, I think good. So that shows some good knowledge. This, I'm going back. This is the regular old autoencoder. And so I just showed it because it's simple. These results are obtained with what's called a VAIM, variational autoencoder inverse mapper. So in fact, I cheated. The latent representation here is much richer. So there's both a sort of generative latent as well as a latent space that actually retains this sort of moment information. That is what I actually used to decode from. But my hope was to be concise and but yes, you can't. I mean, so you can use this structure and do the same sort of exercise. The problem though is that you don't, in this simplest autoencoder realization of the idea, you don't have, as we would say, sort of a a tractable latent space where I can meaningfully say, like, now let me sample. I give you these moments and now let me decode from them to this. So you couldn't quite do this exercise as such in I think as meaningful a way with just the simplest architecture shown here. But yeah, the real results are from this richer structure. So that's a very good question. Do you work on the subject or is it?
Yeah.
Yeah.
Mostly machine learning.
Excellent. Yeah, so we should talk then. Maybe. Okay, cool. Yeah, thank you.
Can you go to slide 21?
Sure.
I think it was.
Yeah, sorry. This thing. Yeah. Okay.
One forward, actually.
One
forward. All right, yeah.
No, that's okay.
No, sorry, one more maybe?
Yeah.
No, so you had the PDFs.
Yeah.
As a function of X. It wasn't this one.
Do you remember the subject?
Roughly, I think you were including EIC pseudo data.
Was it that?
Showing the impact.
Okay, maybe back then.
Yeah, this one. So
This
it's
thing.
this gray rectangle on the left here, at the low ends.
Oh, yeah, I think that's right. I think the great, yeah, you're quizzing me. I think the I think the gray rectangle was just to block out I think where the data actually were turned on. I think the data set that we included. So I think if I'm recalling correctly, I can get back to you in case I tell you something wrong. But my recollection was that we simply wanted to block out kind of the extrapolation region to make clear sort of where the data actually lived. But this is from a few years ago, so I'd have to double check. But that's my recollection, I think. So yeah, we can talk about it more, of course. But, yeah.
Excellent.
Yeah.
I think that's a nice point. So we'll stop here and thank Tim again for his lectures. Let's hear tonight first for our presentation sessions, and let's have a 15-minute break or half an hour. So 15 to the boss. I'm not the boss. All right. 20 to 11. Let's do this. All right. Have a little bit less than half an hour break.
How you went outside?
Yes. He was ready. Hey,
good.
good to see you.
Summer.
Yeah. No. I need a break from having the.
I spent 2 weeks there.
7 to 8 hours a night.